Through a small telescope on a clear night, a globular cluster appears as a smear of pale light caught between stars, softly rounded at its edges, brighter at the center in a way that no amount of focusing will sharpen. It does not resolve. It sits there, patient and faintly luminous, like breath condensed against cold glass. The surrounding stars are points. This thing is not a point. It holds its shape, a gentle sphere of unresolved glow, compressed at its heart and fading gradually toward the dark, hovering in the eyepiece like something ancient and entirely self-contained. That soft appearance is not a failure of the instrument. What the eye is meeting, even through a modest lens, is the combined light of tens of thousands of stars, packed into a volume of space so small, at such a remove, that their individual lights blend into one pooled shimmer. The cluster is not close, it is not dim. It is both very far away and very densely occupied, and the result is this: a cotton ball blur with a heart that refuses to empty, burning quietly at the center of its own gravity. Move the telescope slowly, and the cluster drifts across the field of view without changing shape, a sphere of ancient light sliding between nearer, younger stars. It will be there again tomorrow night. It has been there in approximately the same position relative to our sky for longer than the Earth has existed. The cluster has a center. That much is clear, even without resolution. Something draws the light inward, not all at once, not to a hard point, but in a gradual brightening that steepens toward the middle and never quite reaches a peak visible from this distance. A ball of cotton with a denser core, a breath that has been held so long it has begun to compress. The brighter center is not an illusion. It reflects something real about how the stars are arranged inside, packed more and more tightly as the eye moves inward from the outer edge, density increasing not in steps, but in a long continuous gradient, from sparse to crowded, to very crowded indeed. Near the outer edge, the glow dims toward nothing over a span of sky that, translated into actual distance, represents many light years. The stars in that outer region are still members of the cluster, still bound to it, still orbiting within it, but widely spaced, each one separated from its nearest neighbor by distances that would feel from inside like open country. A traveler moving outward through those loosely scattered suns would pass from one to the next over intervals measured in fractions of a light year, the rest of the cluster pulling at them from behind with a gravity that grows fainter but never quite releases. This is where the cluster breathes, where its gravitational hold thins to its most delicate, and where the boundary between membership and escape is not a wall, but a slow gradient, fading like the last syllables of a long sentence, the brightness of the outer edge, the deepening of the center. These are the visible signs of a structure built entirely by gravity, shaped over billions of years into something very close to a sphere. The shape itself is worth dwelling on. A sphere is what gravity makes when it has enough time and when nothing else is pulling too hard in any one direction. Given long enough, a cloud of stars held by their mutual gravity will settle into approximate spherical symmetry, the orbits of the individual members filling out the available space in all directions more or less equally. What the telescope shows, that near-perfect roundness, that uniform thinning in every direction from the center, is not an accident or an artifact. It is the product of billions of years of gravitational adjustment, each star orbiting, each orbit precessing, the whole system slowly losing its original asymmetries and settling, as heavy things settle, into the quietest available shape, a shape that ancient, that patient, that complete, carries a particular quality of stillness in the eyepiece. The stars inside a cluster span an enormous range in type and color and brightness, though none of that is visible through a small telescope. Through a large one, or in the images made by instruments in orbit above the atmosphere, the blur begins to break apart. The outer regions of a nearby cluster resolve first, separating into individual points of light, amber, pale orange, yellowish white, distributed across the frame like a slow scatter of warm embers. Closer to the center, the stars grow too numerous and too close together for easy separation, even at the full resolution available through the sharpest instruments ever built. The inner core of the densest clusters remains a dense shimmer, the individual stars crowding against one another in the image as they crowd against one another in space. A nearby cluster imaged by such an instrument reveals the full range of its population. There are deep amber red points, warm and swollen. There are softer yellow stars, slightly smaller and dimmer. There are pale white ones. There are cooler orange ones scattered through the outer regions like coals that have had time to dim. The range of color across a single cluster spans something like the range of colors visible in a bed of fire, seen through a long evening, reds and yellows and warm whites, when each one a sun of a different temperature and a different phase of its long life, gathered by chance and gravity into a single sphere. The density of stars toward the center of that image, the count of points per small area of sky, increases in a way that is not intuitive from the outside. In the neighborhood of our own sun, the nearest star is roughly 4 light years away. In the outer regions of a typical globular cluster, that figure might fall to a fraction of a light year between neighbors. In the core, it falls to something far smaller still, sometimes to separations measured in a few weeks' worth of light travel, distances so small on a stellar scale that what is ordinary space outside the cluster becomes a very crowded place inside it. A night sky seen from a planet in the outer region of a globular cluster would already be strange. The ordinary darkness of deep space would be replaced by a sky carrying hundreds of stars bright enough to cast shadows and dozens bright enough to read by. Not the dark and mostly empty dome visible from Earth, where the nearest star is a faint point and the naked eye at its best can make out a few thousand suns. A sky populated closely and warmly by neighbors. A sky that did not fully darken because there were always enough nearby suns on any side to keep the horizon and the zenith in a kind of low, soft glow. From the inner core, the sky would cease to have anything in common with what is visible from our world. Thousands of stars would burn against a background of thousands more. The space between them would be light rather than dark, a continuous brightness, stippled and layered, stretching in every direction, a sky without a dark patch large enough to notice. Standing on a planet within that core, if such a place could exist in the long run, which is not certain, the darkness that a sleeping mind associates with night would simply not be available. The universe, seen from inside the heart of a globular cluster, is a place made mostly of light. That kind of density, stars separated not by light years, but by light months or light weeks, is what the name globular cluster carries inside it. Not a loose scattering, not a region where stars happen to be slightly more common. A true concentration, a gravitational city where the population per unit volume is millions of times greater than in the quiet galactic neighborhood where our own sun drifts. Millions of times, not twice, not 10 times, not even 1,000. In the densest cores of the densest clusters, the local density of stars exceeds what surrounds our own sun by factors that are difficult to step through slowly. The closest comparison is not other stellar environments, but something more like the difference between walking through an empty field and walking through a crowded city square, except that the square is itself made of suns. The boundary of a globular cluster is not sharp. There is no wall, no membrane, no change in the character of space as such. What changes, moving outward from the core, is simply the number of stars per unit volume and the strength of the gravitational pull directed back toward the center. The transition from cluster to open space is gradual, a thinning, a loosening, a slow release, until the last few outlying members are separated from one another by gaps wide enough that from the outside they might not look like members at all. The cluster tapers into the surrounding dark, the way a voice tapers into silence, smoothly and without a hard stop. But the surrounding dark is itself not empty. Spread across the vast space surrounding our galaxy, extending outward to distances of tens of thousands of light years, in every direction from the galactic center, there is a halo of stars, individual stars, not gathered into any cluster, not bound to any particular neighborhood, simply distributed, loosely and thinly, through an enormous sphere of space that envelops the flat disk of the galaxy like a fog. These are old stars, most of them chemically similar in some ways to the stars inside the clusters. They are ancient, they formed early, but they are not clustered. They are alone, each one separated from its nearest neighbor by the ordinary vast distances of interstellar space, drifting on long orbits that carry them through the halo with no particular grouping, no gravitational community, no shared address. From inside the disk of the galaxy, these halo stars are almost invisible to casual observation, too sparse, too scattered, too individually faint against the general glow of the galactic plane. They are there in great numbers, but their numbers are spread across such an immense volume that any given small region of the halo holds almost nothing. A night spent looking into that space would show very few of them, each appearing as just another faint point against an already faint background. The halo is old, and it is large, and it is almost entirely empty by any standard that involves touching or being near anything. The globular clusters orbit in that same halo. They move through it, following long, slow paths that carry them above and below the galactic plane over timescales of hundreds of millions of years. In that respect, they share a neighborhood with the halo stars, the same general region, the same ancient age, the same orbital territory around the galaxy's center. But a globular cluster moving through the halo is not the same kind of thing as a halo star moving through the halo. The halo star is alone. The globular cluster carries with it, across all of that empty space, a gravitationally bound community of tens of thousands or millions of stars, packed densely enough that its internal structure persists across billions of years of travel. The cluster is coherent. It has a center, it has an inside, it has a boundary, diffuse and gradual, but real, where its gravity still draws its outermost members back and inward. The halo star has none of this. It has no companions in the local sense, no shared gravity holding it to any of the other halo stars around it. It travels alone through space that is so thoroughly empty of close neighbors that the sky visible from its surface, if it has a surface, would look much like the sky visible from our own sun, dark, vast, and full of very distant things. The contrast between these two conditions, the solitary halo star adrift in its enormous quiet, all, and the globular cluster crossing the same space with a million companions bound together in a sphere, 100 light years across, is a contrast between two very different answers to the same ancient conditions. Both formed early, both are old, but one dispersed and one did not. To look at a globular cluster through a telescope is in part to look at something that held together when it might have spread apart. The gravity of these objects was sufficient, even over billions of years, and across the disruptive passages through the galactic plane and the tidal forces of the galactic center, to hold them intact. Other groupings of stars did not hold. Open clusters, younger, looser, less massive, bound by a weaker collective gravity, form and dissolve on timescales of a few 100 million years at most. They are temporary concentrations of young stars that share a birth cloud and a birth moment, and then drift away from one another as the galaxy's tidal forces and the slight randomness of each star's individual orbit pulls them apart. By the time a star like our Sun reaches middle age, its birth cluster has long since ceased to exist as a recognizable structure. Its former neighbors have dispersed into the general field of galactic stars, each following a different orbit, separated by distances that will never close again. The Pleiades, visible to the naked eye as a tight group of young blue-white stars, are an open cluster of this kind. They are only about 100 million years old. They contain perhaps a few hundred stars, loosely arranged, their mutual gravity already insufficient to prevent the slow dispersal that will, over the next several 100 million years, scatter them individually into the disk. They are bright and young, and they will not last. As structures, they have no dense core. They have no steep brightness gradient from center to edge. They do not glow with the deep amber light of old swollen stars. They are temporary. A globular cluster seen in the same sky as the Pleiades, and on a clear night one is sometimes visible not very far from them, is something qualitatively different, older by a factor of more than 100, bound by a gravity that the Pleiades cannot match, carrying stars that have had time to age through stages of their lives that the young Pleiades stars have not yet reached, still spherical, still coherent, still holding its center after a span of time so long that if it were compressed into a single year, the lifetime of the open cluster visible beside it would occupy about 3 days. The difference in binding, the reason one holds and the other disperses, comes down to mass and density and the depth of the gravitational well at formation. A globular cluster, formed in one rapid burst from a single enormous cloud of gas collapsing in the early universe, assembled enough mass in a compact enough volume to generate a gravitational potential deep enough to hold its members despite all subsequent disturbances. An open cluster assembled more gently, more recently, from a less extreme collapse, never achieved that depth. Its members drifted away not because they were pushed, exactly, but because the gravitational thread connecting them was never strong enough to hold permanently. The result, after billions of years of galactic history, is that the open clusters visible in the sky today are all young. There are no old open clusters, because the old ones are gone. The globular clusters are all old, because it is precisely their age, their origin in the dense, turbulent early universe, that gave them the mass and density to survive. This is a feature of the observable sky worth sitting with for a moment. Every loose, scattered group of stars visible in the galactic disk is young. Every compact, spherical, densely populated sphere orbiting in the halo is ancient. The two categories do not overlap. The sky is arranged, in this respect, as neatly as a library sorted by age, the young books stacked loosely on the main floor, the ancient ones preserved and condensed in a separate room above. A globular cluster, seen from the outside, from a distance of thousands of light years, does not call attention to this arrangement in an obvious way. It appears as a soft smear of light, spherically symmetric, brightening toward the center, fading gradually at the edges. It appears, in fact, very much the way it appears through a small telescope on a quiet night, a cotton ball of ancient light, self-contained and undisturbed, moving slowly across the sky, background on the immense timescale of its orbital period. But what the appearance encodes, sitting inside that unresolved glow, is billions of years of gravitational patience. Every star in that cluster has been orbiting within it since the cluster formed. The sphere itself, its shape, its density gradient, its steep inner brightness is the product of countless billions of orbits completed, of stars passing close to one another and adjusting their paths by small amounts, over and over and over, until the ensemble of all those small adjustments has sculpted the original cloud of gas and young stars into something close to perfect symmetry. A sphere that old, that gravitationally sculpted, that patient, is a kind of relic, not a fossil exactly. The stars inside it are still burning, still orbiting, still interacting, but a preserved structure, one whose shape and coherence and survival constitute a record of conditions that no longer exist anywhere in the present-day universe. The molecular clouds that formed these objects no longer exist. The density of the early intergalactic medium that allowed them to form no longer obtains. The conditions under which millions of stars could ignite almost simultaneously within a single collapsing region passed billions of years ago and will not return. What remains is the sphere. It hangs in the eyepiece of the small telescope, cotton ball soft, slightly brighter at the heart, hovering against the dark as though it has been there forever and plans to continue. The surrounding stars, nearer and younger and scattered without pattern across the field of view, are each alone. They move on independent orbits. They share no history with one another and no gravitational future. They are the halo, diffuse and individual, every one of them a single sun, adrift in a vast quiet space. The globular cluster among them is none of that. It is bound, it is centered, it is a sphere of 1,000,000 old suns, each one tied to the others by gravity that has held through more orbital periods than the mind moves through easily, each one completing another slow pass around the common center, while the halo stars around them continue their long solitary drifts through space. One thing is spread thin, the other is gathered close. Both are ancient, both are still. The cluster persists inside the halo, the way a stone in a river persists, the water moving around it, diffuse and individual, while the stone holds its shape, holds its center, holds its ancient density against the long, slow current of time. The eyepiece holds them together, the diffuse and the gathered, the solitary and the communal, the halo's uncountable individual stars, and the cluster's single coherent sphere, both ancient, both quiet, both continuing, one distributed across a silence that has no edge, and one compressed into a glow barely wider than a breath, just bright enough to find in the dark. It has been there a very long time. It will be there tomorrow night, and the night after, and for nights not yet countable, slowly orbiting, slowly breathing, holding its 1,000,000 stars in their ancient gravitational embrace, a sphere of old light pressing softly against the dark, while the rest of the halo drifts, solitary and wide, in every direction around it. The telescope does not resolve it fully. The center refuses to open into individual stars at this distance. From this ground, with this instrument, the glow simply deepens, and then deepens a little more, and then holds. It is enough. The shape is whole. The gravity is there, invisibly, doing the work it has always done, drawing every star in the cluster back toward the center it has always had. the center that was there when the first light of this sun reached the first eye that ever looked up, and before that, and before that, and before. The surrounding dark is very large. The cluster is very small inside it, 100 light years across, perhaps, in a halo that spans 100,000. And yet, from this distance, in this eyepiece, it is the cluster that catches the eye, the cluster that holds the gaze, the cluster that has a center and a structure and a shape that persists. The diffuse halo around it is everywhere and invisible. The cluster is here, and round, and glowing, and old, and still. It drifts slightly in the eyepiece as the Earth turns beneath the telescope, carrying the observer and the instrument, and the small circle of sky together through the night. The cluster moves with the stars, and the stars move with the planet, and the planet moves through a galaxy that contains the cluster, and the cluster moves through that galaxy in its own slow and ancient arc, and all of it continues, unhurried and indifferent to the hour, the way things that have been old for long enough have learned to simply continue. The cotton ball glow does not sharpen, the center does not resolve. The edges thin and thin and thin, and then are gone, and where the cluster ends and the halo begins is not a line but a softness. The same softness visible in the eyepiece, the same gradual release, a city of ancient stars quietly dissolving at its edges into the enormous, silent, individual dark. In the first moments of the universe, before any star had cooled to steadiness, the gas was everywhere and restless. It pressed against itself. It compressed and heated and fell inward along invisible lines of gravity, and in the densest places where the hydrogen was thickest and the collapse fastest, great turbulent clouds took shape that had no equivalent anywhere in the cosmos that exists today. They were not quiet, they churned. Their inner pressures were enormous, their temperatures rising fast, their boundaries unstable and constantly renegotiating with the surrounding dark. From regions like these, the first generations of stars were already beginning to ignite, small bright points scattered through the collapsing mass, each one a core that had grown dense and hot enough to begin fusing hydrogen into helium and releasing the light that would define it for billions of years. Some of those clouds were so massive, and their internal pressures so extreme, that they did not fragment gently into scattered individual stars. They shattered. Hundreds of thousands of stars ignited nearly at once within a single collapsing volume, so close together that their gravitational fields overlapped and tangled from the moment of their birth, binding them into a single coherent object before any of them had time to drift apart. The cluster was already a system before any individual star within it knew it was not alone. That is roughly how it began, not in silence and not slowly. In the compressed and violent dark of the early universe, in conditions of pressure and turbulence that have not existed anywhere since, the oldest stellar cities were born all at once in a single catastrophic flowering of light. The clouds that produced them were composed almost entirely of hydrogen and helium. This was not a limitation of the clouds themselves, but a fact about the age in which they existed. The universe was young, the great cycle of stellar life, in which stars forge heavier elements in their cores, explode, and scatter those elements into the surrounding gas, enriching it for the next generation, had barely begun. Oxygen had been made in only the smallest quantities. Carbon was a trace. Iron was nearly absent. The periodic table, as it existed in those early clouds, was almost entirely the first two rows, and everything below that was so rare as to be nearly invisible against the overwhelming mass of the simplest atoms. The stars that formed from these clouds carry that composition still, because stars spend their entire main sequence lives burning hydrogen in their cores, while their outer layers remain largely unchanged. The surface chemistry of an old star records the chemistry of the gas from which it was born. The stars inside the most ancient globular clusters are made of material that is by mass nearly 1,000 times poorer in iron than the Sun. Not slightly iron poor, profoundly, almost totally iron poor. When astronomers measure the ratio of iron to hydrogen in their atmospheres and compare it against the Sun's, the numbers fall far below any star that could have formed in a chemically enriched galaxy. These are stars built from the original inventory of the cosmos, before any of the great supernovae had time to seed the interstellar medium with the elements that later generations would take for granted. The term for this poverty of heavy elements is metallicity, and in astronomy, metal means anything heavier than helium. In ordinary language, a metal is a hard and shining solid. In the language of stellar physics, a metal is any element that the early universe did not produce in abundance, and that had to be built inside a stellar interior and scattered across space in an explosion before the next generation of stars could inherit it. The low metallicity stars of ancient globular clusters predate most of that inheritance. When they were born, the universe's supply of these heavier atoms was only a thin dust above nothing. They fused hydrogen, they built helium in their cores, and in their outer layers they preserved, essentially unaltered, the chemical state of matter as it existed at the beginning of everything. There is a particular image that helps locate this in time. Imagine the universe as a river, long and wide, moving slowly from its source toward wherever it is going. Near the source, the water runs cold and clear and carries almost nothing in it. No sediment, no minerals dissolved from eroding stone, nothing the current has picked up along the way. The stars that formed near that source are like water drawn from it before the river had time to gather anything. They are old in the way that pure water is old, unchanged, carrying almost nothing of what came after, still essentially what they were at the beginning. The clusters those stars inhabit are, most of them, between about 8 and 13 billion years old. The universe itself is approximately 13,800,000,000 years old. The difference between those numbers is small. The oldest globular clusters formed when the cosmos was, by its own reckoning, still very young, perhaps only a few 100 million years old, perhaps a little more. The exact timing varies by cluster and by the method used to measure it, but the general picture is settled. These structures were already ancient when the sun was a cloud of gas, when the earth was not yet a solid thing, when the solar system had not yet begun the slow accumulation that would eventually produce, among other things, the quiet room in which someone now lies listening to the night. There is a method for determining cluster ages that does not require measuring radioactive decay or performing any chemistry on the stars themselves. It reads from a diagram. In the middle of the 20th century, astronomers developed a way of plotting a cluster's stars by their temperatures and their luminosities, and this plot, called a Hertzsprung-Russell diagram, after the two astronomers who independently developed its basic logic, reveals something that clocks can confirm. Stars that are fusing hydrogen in their cores settle onto a long diagonal band in the diagram called the main sequence, and they stay there, slowly brightening over their lifetimes until the hydrogen in their cores runs out. When the core hydrogen is gone, the star changes. It expands, brightens dramatically, and moves off the main sequence toward the upper right of the diagram. This departure from the main sequence is called the main sequence turnoff. What makes this useful for measuring ages is that massive stars exhaust their core hydrogen much faster than small ones. A star 10 times the mass of the Sun may spend only a few tens of millions of years on the main sequence before turning off. A star like the Sun spends around 10 billion years. A star half the mass of the Sun may remain on the main sequence for longer than the current age of the universe. In a cluster where all the stars formed at essentially the same moment, the massive stars turn off first, and the smaller ones remain on the main sequence for longer. The current position of the turnoff, the luminosity and temperature at which stars are just now beginning to exhaust their core hydrogen and move toward the red giant region, depends entirely on how much time has passed since the cluster formed. In a young cluster, massive hot stars are still on the main sequence, and the turnoff is bright and blue. In an old cluster, those massive stars are long gone, and only the cooler, less luminous stars near the solar mass range are still burning steadily. The turnoff sits lower and cooler. By reading the turnoff position against theoretical models of stellar evolution, astronomers can determine how long the cluster has been alive. The precision is not perfect. There are uncertainties in the models and in the measurements, but it is sufficient to place the oldest Milky Way clusters firmly in the range of 11 to 13 billion years. That number is significant. It is close enough to the age of the universe, as determined by the cosmic microwave background and the expansion rate of space, that it serves as an independent confirmation of the standard cosmological picture. A universe that was only 10 billion years old could not contain clusters aged 12 billion years. The consistency between the two numbers is itself a piece of evidence that the broader framework of cosmology is correct. Not all globular clusters are the same age, and not all of them formed under the same conditions. There is a pattern visible across the full population of clusters surrounding the Milky Way, a tendency for the cluster population to separate, broadly, into two groups. One group is very metal poor, with iron abundances far below solar. These clusters are concentrated in the outer reaches of the galaxy's halo, moving in orbits that are often tilted steeply relative to the galactic disk, some of them retrograde, traveling in the opposite direction from the general rotation of the galaxy's stars and gas. The other group is slightly less metal poor, still ancient by any ordinary measure, but chemically a step ahead of the first group, as though the gas from which they formed had already been through at least one round of enrichment by dying stars before they ignited. The chemical difference between the two groups encodes a difference in history. The very metal-poor clusters formed earliest, in conditions closest to the raw state of the early universe, before any significant chemical enrichment had taken place. The slightly less metal-poor clusters formed a little later, after some fraction of the first stellar generation had already completed its life, exploded, and scattered heavier elements back into the gas. Both populations are old by any terrestrial standard. The difference between them is measured in chemistry rather than years, but chemistry, read carefully, is time. Some of those clusters, the evidence now suggests, did not form inside the Milky Way at all. Galaxies grow by consuming smaller galaxies. The Milky Way as it exists today is larger and more massive than the Milky Way that existed 10 billion years ago, and it became larger by attracting, pulling in, and absorbing dwarf galaxies, small, loosely bound collections of stars and gas that moved too close and were torn apart by the gravity of the larger system. When a dwarf galaxy falls into a larger one, it does not dissolve instantly. It is stretched and deformed, its stars pulled into long tidal streams that wrap around the larger galaxy's halo for billions of years before dispersing entirely. But its densest concentrations, the globular clusters it carried with it, are gravitationally compact enough to survive the disruption. The dwarf galaxy's disk is gone. Its gas has been swept away. Its scattered stars have merged into the halo of the absorbing galaxy. But its globular clusters continue to orbit, intact, carrying their ancient chemistry and their tilted eccentric orbits as the only coherent remnants of a structure that no longer exists. There is something very still about that image. A dwarf galaxy, formed early in the history of the universe, assembling its stars and its clusters over billions of years, moving through the dark, and then at some point drawn too close to a larger mass and pulled apart over hundreds of millions of years. Its components scattered, its identity dissolved. Nothing survives of its original form except the densest objects it contained. Those objects continue to orbit. They do not know they are orphaned. They carry no record of having belonged to something that is gone, except the chemistry of their stars and the angles of their paths. The Milky Way may have acquired a substantial fraction of its inner halo globular clusters this way, not growing them internally, but inheriting them from smaller systems. The orbits of these clusters, measured with great precision in recent years, tend to be tilted and eccentric in ways that do not match the rotation of the galaxy's disk. They are moving as their original host galaxies were moving at the moment of capture, their paths not yet smoothed into the general flow of the Milky Way's disk. In this sense, the spatial distribution and the motion of the cluster population is a kind of compressed archive, a record of collisions and absorptions that happened when the galaxy was still assembling itself, encoded in the current positions and velocities of objects too compact to have been erased. Inside those objects, the stars are old enough to have outlasted everything that surrounded them at birth. The clouds from which they formed are long gone. The gas that filled the space between them has been heated and dispersed by the radiation of the stars themselves and by any supernovae that went off in the cluster's early history. The interstellar medium that once connected this cluster to others and to the larger structure of whatever galaxy or filament it formed within is now entirely absent. The cluster moves through space as a nearly closed system, its stars still bound to one another, their orbits still determined by the same gravity that has governed them for 11 billion years, the whole sphere rotating slowly and drifting through the halo of the Milky Way on an orbit that may take hundreds of millions of years to complete. The turbulence that created these clusters is one of the central open questions in their study. There are several ways to produce a region dense enough to collapse into hundreds of thousands of stars at once. One involves galaxy mergers, the collision of two large gas-rich systems at a time when the universe was young and such collisions were common. In the shock front, where two galaxies interpenetrate, gas is compressed to densities far beyond what either galaxy could achieve on its own, and the collapse into stars can be extraordinarily rapid and efficient. Another possibility involves the extreme compression of gas in the dense filaments of the early cosmic web, the large-scale structure of dark matter and gas that pervades the universe and along which galaxies assemble. In both cases, the essential condition is the same, a very large mass of cold, dense gas, compressed faster than it can fragment into ordinary individual stars, forced to collapse and ignite on a scale that produces a gravitationally bound city of suns, rather than a scattered field of them. The fact that clusters formed through these events at all is not obvious. Most of the gas in a collapsing cloud does not end up in stars. It is heated by the radiation of the first stars to ignite, by shock waves from any early supernovae, and by the momentum of the collapse itself. In ordinary star-forming regions in the present-day universe, only a few percent of a cloud's mass actually reaches stellar density and ignites. the efficiency is low. But the clouds that produced globular clusters seem to have converted a much larger fraction of their gas into stars, perhaps 20 or 30%, perhaps more in the densest cases, and they did it quickly enough and in a small enough volume that the stars they produced remained gravitationally bound to one another, rather than dispersing into the surrounding galaxy. This high efficiency, in conditions no longer found in the modern universe, is part of why globular clusters have no close analog in the present-day cosmos. The environments that produce them are gone. The cluster that resulted from such a collapse would have been, in its earliest moments, very different from the quiet sphere it is today. The first few 100 million years of a globular cluster's life are violent. The most massive stars, which also have the shortest lives, burn through their hydrogen in tens of millions of years and explode as core collapse supernovae, releasing enormous amounts of energy into the surrounding gas. Their shock waves heat and expel the residual gas that was not converted into stars, clearing the cluster of the raw material that could have produced more stars. The radiation from the most luminous massive stars ionizes the surrounding hydrogen, driving off any diffuse gas before supernovae even have time to act. For a period, perhaps the first 100 million years, the cluster is louder, brighter, and more disordered than it will ever be again. Then, the massive stars are gone, the supernovae stop. The expelled gas disperses into the larger galaxy, carrying with it the heavy elements the massive stars forged in their cores and scattered in their deaths. The stars that remain are the longer-lived ones, the low-mass stars that will spend the next 11 or 12 billion years burning hydrogen steadily, changing slowly, remaining present long after everything violent and transformative has happened. The cluster quiets, it settles, its stars begin the long process of organizing themselves gravitationally, faster stars exchanging energy with slower ones, the whole system relaxing toward a kind of statistical equilibrium that takes billions of years to approach and is never fully reached. What remained after that initial violence is what can be seen today. The cluster is quieter now, not silent. Stars are still evolving, still moving, still exchanging gravitational energy in every encounter, but operating on timescales so long that from any single moment of observation it appears nearly static. The sphere hangs in space. Its stars circle one another in orbits so slow that no human observation has ever captured more than an instant of their movement. The whole structure drifts through the Milky Way's halo on its long orbit, indifferent to the passage of individual human lifetimes, indifferent to the existence of the planet from which it is observed, indifferent in the way that only very old and very large things can be. The chemistry of the stars records the youth of the universe. That is the fundamental thing. Every star in an ancient globular cluster was formed from gas that had barely been processed, gas that contained almost nothing except what was produced in the Big Bang and in the very first round of stellar death. And because the outer layers of low-mass stars do not change dramatically over their main sequence lifetimes, the surface composition of a cluster star today is essentially the surface composition of the gas cloud from which it formed, preserved across more than 10 billion years. This matters because it makes the stars into archives. Not archives in a metaphorical sense, but in a literal physical one. The light leaving a cluster star carries, encoded in its spectrum, a record of the elemental abundances present in the early universe. An astronomer measuring the iron content of a cluster star is measuring the iron content of the gas cloud that collapsed to form the cluster, which is measuring the state of the interstellar medium in the Milky Way's earliest history. which is measuring how far the universe had progressed in building heavy elements at the time the cluster formed. These are not separate measurements, they are the same measurement, made possible by the fact that the star has preserved the record without alteration. The extremely low iron abundance of the oldest clusters means they formed before the Milky Way, or whatever system they originally inhabited, had accumulated significant quantities of iron-producing events. Iron in the interstellar medium comes primarily from a specific class of stellar explosion called a Type 1a supernova, which requires a certain time delay after initial star formation to produce. The very low iron measured in the oldest clusters means there had not been enough time for this delay to pass. The stars that eventually produced these delayed explosions had not yet completed their lives. The universe was too young. What was present in the gas was mostly the products of the fastest stellar deaths, the core collapse supernovae of the most massive stars, which go off quickly and produce large amounts of oxygen, magnesium, and silicon, but relatively little iron. The chemical signature left in the oldest cluster stars is therefore not just a record of low metallicity in general. It is a record of early universe chemistry specifically, dominated by rapid enrichment from massive stellar explosions, not yet augmented by the slower iron contributions that would come later. That distinction is subtle, but important. It means the composition of the oldest cluster stars does not merely tell us that they are old. It tells us something about the rate and sequence of early cosmic enrichment, about the timing of stellar generations, and the intervals between stellar deaths. The stars are not passive relics, they are records of a process, and reading them carefully enough yields not just an age, but a kind of chemical history of the first billion years. The low metallicity signature also has a practical consequence. Because the oldest cluster stars formed from gas that was so chemically simple, their interiors evolved differently from the interiors of more metal-rich stars. Opacity, the degree to which a stellar interior resists the outward flow of radiation, depends in part on the abundance of heavy elements. A metal-poor star is slightly more transparent to its own radiation, which affects how energy moves through it, how it burns, and how it ages. The theoretical models used to calculate a cluster's age from its Hertzsprung-Russell diagram must account for this, and they do, which is one reason the age estimates for the oldest clusters have been refined steadily over the decades as the models have improved. The refinement is ongoing. Cluster ages derived from the turn-off point are not single fixed numbers, but estimates with ranges, and the ranges reflect genuine uncertainties in the models, in the distance measurements needed to convert apparent brightness to true luminosity, and in the measured chemical abundances of the stars themselves. The current best estimates for the oldest Milky Way globular clusters, NGC 6397, and a handful of others of similar age and metallicity, place them between about 11 and 13 billion years old. The range is not a sign that the method is weak, it is a sign that the method is honest, carrying its own uncertainty rather than hiding it behind false precision. 13 billion years is a number that sits at the edge of human comprehension, not because it is incomprehensibly large in abstract terms, but because there is nothing in ordinary experience that scales to it. The deepest roots of the oldest trees on Earth reach back a few thousand years. The oldest rocks recoverable from the continental crust are around 4 billion years old, already old enough to be meaningless to the nervous system. 13 billion years is more than 3 times that. It is time enough for the sun to have formed, lived for 5 billion years, and dissolved, and still leave 2 billion years of the cluster's history unaccounted for. The cluster existed before the sun. The cluster existed before the earth. It existed before the solar system was a cloud of gas, before that cloud had condensed from a larger structure, before that structure had separated from the general flow of the early galaxy. The cluster was old by the time any of this happened, and the stars inside it were already set in their courses, already burning at their steady, slow rates, already locked in the gravitational embrace that would hold them together through everything that followed. The galaxy around them changed, mergers happened, new stars formed in the disk below. The sun ignited and warmed its system of planets. On one of those planets, things emerged that could think and ask questions and build instruments sensitive enough to measure the iron in the spectrum of a star 45,000 light years away and determine, from the near absence of that element, that the star formed when the universe was less than 2 billion years old. The cluster does not know this. The stars inside it do not know that they are ancient. They burn at the rate their mass and composition require them to burn, and they will continue doing so for billions of years more. The low-mass stars among them, the ones that have barely changed since the cluster formed, will still be on the main sequence long after the sun has exhausted its own hydrogen and swollen into a red giant and faded. They carry their antiquity in their composition, not in any visible sign of age. They are not withered. They are not decayed. They are simply, in the deepest possible sense, old, old in the way the light from them is old by the time it reaches us, old in the way the atoms that make them are old, having been present in the universe since before most of what now exists had come into being. The stars themselves are poor in iron. That single fact contains multitudes. It means the universe had not yet cycled through enough stellar generations. It means the cluster formed early, in an environment close to the raw beginning. It means the gas from which those suns condensed was almost entirely the first material, hydrogen falling inward, helium compressed alongside it, and almost nothing else at the atomic level that our own blood or bones or the iron core of this planet would recognize. The stars built themselves from what was available. They fused hydrogen, they built helium in their interiors, and they preserved in their outer layers the chemical record of a universe that had barely begun to complicate itself, a universe still close to its own simple beginning. That record persists. It persists in the spectra of stars that have been burning for 11 billion years and will burn for billions more. It persists in the ratios of elements, in the precise degree of iron poverty measured in absorption lines, so faint that reading them requires hours of observation with instruments far more sensitive than any human sense. It persists because the universe wrote it there, early, in the only medium it had available, the composition of matter itself, and because the stars that received the inscription have held it without change across the whole intervening length of cosmic time. The cluster drifts on its long orbit through the halo. The stars inside it burn slowly and steadily, their outer layers carrying the chemistry of the early universe like a message written in a language that takes a spectrograph to read and a lifetime of study to understand. The gas from which those stars were born is long gone, scattered and mixed into the larger galaxy, enriched and re-enriched by successive stellar generations, transformed beyond recognition. But the stars themselves remain. They carry what they were given at the beginning, and in the faint pattern of absorption lines crossing their spectra, in the precise near absence of iron, in the trace of oxygen, in the signature of a universe still forming its first heavy atoms, the earliest chapter of cosmic chemistry is preserved, still readable, still there, patient and complete. Somewhere near the middle of a globular cluster, Deep within the graduated brightness of its inner regions, a single star burns with the deep amber glow of something very old and very large. It is not the same star it was when this cluster was young. For billions of years, it held itself steady, burning hydrogen quietly at its core, not much different in that long stability from the star we know as our own sun. But now, its core has run through all the fuel it began with, and in response to that depletion, the star has done what stars of its kind always do. It has expanded, slowly over millions of years, into something vast and luminous, a red giant swelling outward, while its surface cools to a color somewhere between deep gold and the low light of a coal left burning in the dark. Its glow reaches the stars around it. It illuminates nothing, not in any useful sense, but it colors the space between its neighbors with a warmth that has been accumulating here, inside this cluster, for longer than the Earth has existed. That amber light is where this story begins. The red giant branch of a globular cluster is not a place but a population. It is a collection of stars at a particular stage of their lives, and within a cluster, they are among the most luminous things present, outshining the quieter, more compact stars that still hold to the stable pattern of hydrogen burning at the core. In the diagrams astronomers use to map stellar populations, plots of brightness against temperature and color. These stars occupy a distinct rising band, a sequence that curves away from the main population and climbs toward greater and greater luminosity as individual stars exhaust more of their resources and respond by growing still larger, still brighter, still more deeply red. The stars ascending this branch are not all the same. They range in luminosity from moderately evolved objects that have only recently left the main body of steady-state burning, up through increasingly bright and inflated structures, until they approach a threshold near the top of the branch where the conditions deep in the stellar core are building towards something much more dramatic than quiet expansion. At the tip of the red giant branch, a star reaches a luminosity of roughly 3,600 times what our sun produces in a single moment of steady output. That specific brightness, the brightness at which the tip is reached, is consistent across clusters, across vast distances, across the whole observable range of these ancient systems. It is not arbitrary. It is set by the physics of helium ignition inside the stellar core, the precise temperature and density at which a new kind of burning can begin. Because that threshold is the same wherever it occurs, the brightness at which it occurs is a reliable marker, a lighthouse at a known height, visible from enormous distances. Astronomers have used it as a measuring stick, comparing the apparent brightness of that tip seen in distant cluster populations against its known intrinsic brightness, and from the difference calculating how far the light has traveled. Distance from a star's last quiet crisis before transformation. The red giant expands slowly. The expansion takes millions of years. From within the cluster, from a hypothetical vantage on some planetary body orbiting a neighboring star, if such bodies exist here, the giant would simply be the brightest nearby object, warming the surrounding space with that long amber emission, drifting through the cluster's crowded interior on the same slow orbital path it has always traced. Nothing in its appearance suggests urgency. Nothing signals what is building at the core, where the ash of burned hydrogen, now helium, has been accumulating, compressing under its own weight, growing hotter in ways that have no immediate visible effect on the surface, thousands of solar radii above. The outside and the inside of a red giant are in a kind of delayed conversation, the slow light from the core taking a long time to work its way through those vast outer layers to reach the surface and then travel on across the space between stars. When the temperature at the core of a red giant reaches the threshold for helium fusion, the ignition does not happen gently. Because the helium core has by then become a degenerate medium, a state in which pressure no longer responds to temperature in the way ordinary gas does. The fusion once started does not regulate itself with the usual feedback. Heat increases the rate of burning, which increases the heat further in a brief cascade that releases an enormous pulse of energy deep within the star. This is the helium flash. It cannot be seen directly from outside. The energy is absorbed by the star's enormous bulk before any of it reaches the surface, and what happens to the visible star is in some ways the opposite of the drama happening at the core. The outer layers contract, the luminosity drops, the temperature at the surface rises slightly, and the star settles into a calmer phase, entirely different from the runaway expansion of the giant branch. The phase that follows is called the horizontal branch. The name comes from where these stars appear in the brightness temperature diagram, not climbing upward like the red giant branch, but spread roughly across a horizontal band at a luminosity much lower than the giant branch tip. These stars have found a new equilibrium. They are burning helium now in their cores, fusing it into carbon and oxygen in a process that is less energetically efficient than hydrogen burning, but stable enough to sustain the star for another 100 million years or so. The horizontal branch is not a single line of identical stars. It is a scatter, and that scatter spans a wide range of temperature. At the cool red end of the branch sit stars with thick hydrogen envelopes still surrounding their helium-burning cores. At the hot blue end, where the temperatures rise to tens of thousands of degrees at the surface, sit stars that have shed much of their outer hydrogen and burn with a paler, more intense light. Between these extremes lies a continuous spectrum of stellar states, all at roughly the same stage of helium burning, but differing in ways that involve both the chemistry they inherited at birth and factors that have not yet been fully identified. The metallicity of the cluster, the fraction of elements heavier than hydrogen and helium contained within the stars at the time of their formation, plays a significant role in determining where a horizontal branch star ends up on that spread. In metal-poor clusters, the ones with the lowest abundances of iron and other heavy elements, the horizontal branch tends to extend far toward the blue end, sometimes reaching extreme temperatures. In metal-richer clusters, stars tend to cluster more toward the cooler end. But metallicity alone does not account for the full range of what is observed. The spread in some clusters is wider than metallicity could explain, and the reasons for this have been discussed for decades without a fully settled resolution. There is a second parameter, and perhaps more than one, that steers a horizontal branch star to one part of the branch or another. Factors that may include the age of the cluster, the mass and rotation of individual stars, or the detailed history of mixing and mass loss during the red giant phase. The question remains open. It sits in the middle of the horizontal branch like a quiet gap in a well-drawn map. Inside the instability strip that crosses the horizontal branch at temperatures close to 6,000 to 7,000 degrees, something particular happens to the stars it contains. The zone in this temperature range is not stable against a specific kind of pulsation. Stars that find themselves in this strip begin to breathe, or rather to oscillate in a pattern driven by the behavior of partially ionized helium in their outer layers. The helium captures energy from the stellar interior during one part of the cycle, heats up and expands, then releases that energy as it cools and contracts, and then begins again. The cycle repeats steadily and regularly on a period that for most stars in this zone runs between a fraction of a day and a single Earth day. These are the RR Lyrae stars, named for the first well-characterized example discovered in the constellation Lyra. An RR Lyrae star, at its brightest, is only a few dozen times more luminous than the Sun. That is not very bright by the standards of a globular cluster, where red giants can outshine it by factors of hundreds. But the RR Lyrae star possesses something more useful than peak brightness. It possesses constancy. The average luminosity over its full pulsation cycle is nearly the same for every RR Lyrae star in every old metal poor cluster, a well-defined intrinsic brightness that does not vary much from star to star. Because of this, any RR Lyrae star observed in a distant cluster carries its true brightness with it as a kind of internal calibration. The apparent brightness as seen from a telescope on Earth is simply the intrinsic brightness reduced by the inverse square of the distance. Measure the apparent brightness, compare it to the known intrinsic brightness, and the distance falls out of the arithmetic with a precision that has been achieved few other ways in observational astronomy. The period of the pulsation is also meaningful. The period is related to the mean luminosity of the star through a well-characterized relationship, so that a measured period is itself a brightness estimate, a cross-check on the direct measurement of apparent magnitude. An RR Lyrae star, oscillating on a cycle of half a day, will have a slightly different intrinsic luminosity than one oscillating on a cycle of 3/4 of a day, and those differences follow a predictable pattern. Every pulsation is a data point. In a single cluster containing dozens of RR Lyrae variables, dozens of independent distance estimates can be made and averaged, and the cluster's distance can be established with a stability that a single measurement could never achieve. The light curve of an RR Lyrae star has a distinctive shape that astronomers recognize at a glance. The rise to maximum light is steep and fast. The decline from maximum back to minimum is slower, more gradual, a long, gentle downslope that takes up more of the period than the quick ascent. The resulting asymmetry, plotted over time, looks less like a smooth wave and more like the profile of a quiet pulse, quick rise and slow fall, repeating without interruption for as long as the star occupies its region of the instability strip, a phase that lasts for the 100 million years of the horizontal branch, give or take the star's eventual departure, as its core helium runs low, and it expands once again toward a cooler and more luminous phase. Globular clusters are rich in RR Lyrae stars. In a metal-poor cluster with a well-populated horizontal branch, dozens of these variables may oscillate simultaneously, each on its own slightly different period, each brightening and dimming independently of its neighbors. From a ground-based telescope sweeping across the cluster on successive nights, the combined light from an unresolved core will show a complicated multi-period variation as different stars reach their individual maxima at different moments. With careful photometry, measuring the brightness of individually resolved stars over many observation sessions, each period can be separated from the rest, each star's pulsation extracted from the ensemble, and the distance confirmed again and again from each independent measurement. The stars that live within a globular cluster also include a population that should not exist. On the brightness temperature diagram of a cluster whose stars all formed at the same time and from the same material, there is a well-defined ceiling for hydrogen-burning stars. Above that ceiling, the main sequence turn-off, no star of the cluster's age should still be burning hydrogen at its core. They should have evolved past that stage billions of years ago. And yet scattered among the population, sitting above the turn-off in the diagram at brightnesses and temperatures that would belong to much younger and more massive stars, there is a small number of objects that do not fit. They are hotter and more luminous than they should be. They look younger than the cluster. They are called blue stragglers. The name captures the strangeness of their situation. They have straggled behind in their evolution, or appear to have done so. A star above the main sequence turnoff of an old cluster is a star more massive than any single star in the cluster should still possess at this age, because all the stars that began massive enough to still be burning brightly at high temperatures should have consumed their fuel long ago and moved on to become red giants, and eventually something smaller and denser still. A star sitting in that region now, a star of apparently high mass still fusing hydrogen at its core, must have acquired that mass from somewhere. It is a second generation object, built not from the original cloud of gas and dust, but from material that passed through other stars first. Two mechanisms can produce a blue straggler. In the first, two stars collide. In the dense inner regions of a globular cluster, the stellar population is concentrated enough that actual physical collisions between stars occur over the cluster's lifetime, not frequently by any ordinary standard, but meaningfully, the probability accumulating over billions of years in a way that adds up to dozens or hundreds of merger events in a single cluster. When two stars meet and merge, the combined body has more mass than either component, and if that mass is sufficient, the merged star takes a position in the temperature luminosity diagram that looks like a younger, more massive star still on the hydrogen-burning main sequence. It is not younger. It is simply heavier than anything in the cluster should be. In the second mechanism, two stars that formed as a binary pair, two suns orbiting one another at close range, evolve at different rates because one is slightly more massive and therefore exhausts its core hydrogen first. As the more massive of the pair swells into a red giant, the outer layers of the giant spill across the boundary between the two stars' gravitational domains and fall onto the surface of the companion. The companion gains mass, it grows heavier. If enough mass transfers, the companion ends up more massive than the turnoff mass, and it sits above the turnoff in the diagram, hotter and brighter than the rest of the cluster's stars, a hydrogen-burning star that looks far younger than the cluster that contains it. The donor star, having given away so much of its outer envelope, may end up as a much smaller helium-rich object, stripped down to little more than a core. Both pathways lead to the same observable result. Both produce blue stragglers. Distinguishing which mechanism has operated in a given cluster, or which is more common across different clusters, has occupied astronomers for many years. The fraction of blue stragglers relative to the cluster population and the distribution of blue stragglers within the cluster, whether they concentrate near the core or spread more broadly through the outer regions, carry evidence about which pathway dominates. Mass transfer events in binary pairs might produce blue stragglers anywhere in the cluster, but direct stellar collisions depend on the stellar density being high enough that close approaches occur, and so collisional blue stragglers should concentrate where the density is highest, in the core. The spatial distributions observed in different clusters do show different patterns, and the patterns shift in ways that suggest the two mechanisms operate at different rates in different environments. Neither mechanism is universal, both are real. A blue straggler in a cluster core is surrounded by stars far older and quieter than itself, stars that have already climbed the red giant branch, already undergone their helium flash, already settled onto the horizontal branch burning their helium in that calmer, steady phase. The blue straggler sits among them, burning hydrogen still, as though it arrived late to the sequence of stellar life that has already advanced so far in everything around it. It is not identical to a young star. Its interior chemistry is different from a star that formed with high mass in the usual way. Its interior is mixed from the material of two other stars, and in some cases, that mixing has produced an object with an unusual distribution of chemical elements, lighter in some ways than its surface temperature suggests, heavier in others. But from a distance, plotted as a point on a diagram, it mimics youth. It sits where youth should sit. The dense inner regions of a globular cluster also produce, over long timescales, a population of unusual stellar pairings that form through a very different process than simple binary formation in a molecular cloud. In ordinary space, binary star systems, two stars orbiting one another, form when the gas cloud that produces a stellar pair fragments in a way that preserves angular momentum between two collapse centers rather than one. These are primordial binaries, pairs that have been in orbit together since the moment of their formation, but in a globular cluster core, the stellar density is so high that the gravitational encounters between passing stars have a measurable probability over many millions of years of creating new pairings from stars that originally had no relationship. A single star passing close to an existing binary may exchange places with one member, ejecting it and taking its place in a gravitational partnership it did not inherit but acquired. The new binary that forms from this exchange may be tighter, more energetically bound than the original, and that tighter binding releases energy that is shared among the surrounding stars, a transaction that occurs countless times across the life of the cluster. The specific pairings that form in cluster cores include some of the densest and most energetic stellar objects known. A neutron star, the collapsed remnant of a massive star that ended its life in a supernova long ago, may capture a companion in the crowded inner regions of a cluster, forming a system in which ordinary stellar material falls onto the neutron star's surface in a slow drizzle of mass transfer. These are low-mass X-ray binaries, and globular clusters harbor them at a rate far higher than would be expected from the cluster's mass alone. The overrepresentation is dramatic. It is an excess that points directly to the formation process, not primordial binary evolution alone, but the dynamical manufacture of new pairings in environments dense enough to make stellar encounters a routine feature of the long, slow years. Some of the neutron stars in these pairings are spun up by the infalling material to rotation rates that sound implausible when converted to ordinary experience. A neutron star is not much wider across than a city, but it holds more mass than the sun. When material falls onto its surface and transfers angular momentum, the star can be accelerated to rotation rates of hundreds of complete turns per second. These are millisecond pulsars, objects that emit beams of radio waves along their magnetic poles and sweep those beams across space with a regularity more precise than the best mechanical clocks humans have built. Globular clusters contain an overabundance of millisecond pulsars for the same reason they contain an overabundance of X-ray binaries, the dynamical formation channel. The cluster core's density is a factory for these objects, producing them far more efficiently than the ordinary galactic field, where encounters between unrelated stars are rare enough to be practically irrelevant on the timescales of a human civilization. The red giant sits in the amber-lit inner regions of the cluster. The horizontal branch star burns its helium steadily at a temperature its metallicity and history conspired to produce. The RR Lyrae star oscillates on its short cycle, brightening and dimming without any assistance, driven by the thermodynamics of its own outer layers. The blue straggler holds a hydrogen-burning equilibrium that should not be possible at the cluster's age, but is possible because the cluster is not simply a collection of isolated stars. It is a community, and material passes between members. And what one star needs another may eventually provide. And the millisecond pulsar spins at the center of a compact binary system it acquired by capture, sweeping its radio beam across the cluster, interior hundreds of times each second. The variety here is something that requires a certain amount of time to settle into. A globular cluster, seen from a distance, looks uniform. From farther still, it is a single point of light. Up close, resolved into its individual stars, it appears as a dense but relatively monotonous city of orange and yellow suns, similar in color, similar in brightness, similar in all the properties visible from the outside. The variety lives inside the individual objects, in the diagrams of brightness and temperature, where the full taxonomy of stellar life is spread out, in the spectra that reveal chemistry, in the timing measurements that expose pulsation and rotation and orbital mechanics. The cluster holds more kinds of objects than any other structure of comparable age in the galaxy. It is old, but old in a way that has had time to grow complex. The horizontal branch extends across its range of temperatures, and at the extreme blue end of that range, there are stars hot enough to emit a significant fraction of their light as ultraviolet radiation. These are the hottest horizontal branch stars, objects whose surface temperatures may exceed 20,000 degrees, burning with a light that shifts well beyond the visible into the ultraviolet, and they contribute to a phenomenon observed in elliptical galaxies and globular cluster populations, collectively known as the ultraviolet upturn, an excess of ultraviolet emission from old stellar populations that was unexpected and took decades to explain. The explanation involves these extreme horizontal branch stars and the related objects that follow from them as the helium in their cores runs low and they begin to evolve along a path different from the cooler stars. They are a minority of the horizontal branch population, but they produce a disproportionate share of the system's ultraviolet output, and their existence was initially read as evidence of unexpected youth in what were thought to be purely old, quietly cooling stellar systems. The coolest and most luminous red giants at the top of the red giant branch lose mass from their surfaces. The outer layers of a red giant are held to the star only loosely, the surface gravity weakened by the enormous radius, and the radiation pressure from the star's luminous core pushes material outward continuously. The mass loss is not fast on any human timescale. It proceeds in a slow stellar wind, material drifting away from the giant's extended surface over millions of years. But it is real, and it is measurable, and it has consequences for the star's later evolution. A red giant that loses more of its hydrogen envelope before undergoing the helium flash will emerge from that flash with a thinner hydrogen layer and will end up on the hotter end of the horizontal branch. A giant that retains more will settle at the cooler end. This connection between mass loss during the giant phase and the temperature reached on the horizontal branch is one of the threads that runs through the second parameter problem without fully resolving it, because the amount of mass lost during the giant phase is itself influenced by factors not yet completely characterized. Near the cluster's outer regions, where the stellar density is lower and the sky viewed from within would show only a few bright companions, rather than the blazing interior visible from the core, there are also stars still burning hydrogen on the main sequence, the lower mass stars that have not yet exhausted their fuel because their mass is small enough that they burn slowly. These stars will outlast the red giants and the horizontal branch stars and the blue stragglers by enormous margins. A star with a tenth of the sun's mass burns its hydrogen at such a low rate that it might sustain itself for 100 billion years or more, a duration that exceeds the current age of the universe by nearly 10 times. These dim red stars carry the bulk of the cluster's total stellar count, but not its light. In a photograph of a cluster, most of the brightness comes from the evolved stars, the giants and the horizontal branch stars, and the blue stragglers, while the true majority of the population quietly occupies the faint, cool, lower end of the main sequence, too dim to see individually from any significant distance. Taken together, the stellar inhabitants of a globular cluster form a population that cannot be found elsewhere in the galaxy in quite the same configuration. Young open clusters lack the red giants and the horizontal branch stars because their stars have not had time to evolve. The general galactic field contains stars of every age and mass, but they are distributed across enormous volumes and rarely encounter one another with the frequency needed to produce blue stragglers through collision or the X-ray binaries and millisecond pulsars that dynamical cluster environments generate. The galactic halo contains old field stars, individually ancient, but scattered across distances so vast that their encounters are essentially zero, their isolation absolute. A globular cluster concentrates all of this, the chemistry of old stars, the evolutionary stages of a population that has been burning through its life stages for billions of years, and the dynamical products of a dense and crowded environment into a volume small enough to study in detail from the distance of tens of thousands of light years. The cluster as a whole is brighter than it would have been when it was young. It would seem intuitively that a stellar population should fade as it ages, as the most luminous stars exhaust themselves and move off the main sequence. And in some respects this is true. The cluster is no longer lit by the massive, intensely blue stars that would have burned through their hydrogen in the first few million years. Those are long gone, leaving behind their remnants, but the evolved stars that have replaced them on the luminosity budget, the red giants, the horizontal branch stars, are themselves highly luminous, and they keep the cluster's total light output at a level that remains considerable across billions of years. A cluster 10 billion years old produces light in roughly the same amount as a cluster of a few billion years, because the loss of high-mass main sequence stars is compensated by the gain of evolved low-mass stars climbing the red giant branch. The cluster does not simply dim. It transforms its light, shifting its overall color toward redder wavelengths, enriching the amber end of the spectrum, while the blue end fades. The RR Lyrae star does not know it is being watched. Its oscillation continues without reference to any observer, the helium in its outer layers moving through its cycle of partial ionization and deionization, energy absorbed and then released. The stellar surface rising and falling by an amount too small to see with the naked eye, but measurable with precision instruments over successive nights. The period of its pulsation, once established, holds steady for long periods of time. Slow changes in the period do occur, and astronomers who track individual RR Lyrae stars over decades sometimes detect these period changes as small systematic drifts in the timing of successive maxima. These drifts carry information about the star's internal evolution, the gradual changes in structure that accompany the slow consumption of the core helium. They are not random. They follow patterns that are consistent with the models of stellar evolution, and reading those patterns in the observed period changes is a way of watching the star age from the outside in real time across a human lifetime. From 30,000 light years away, A distance not unusual for a Milky Way globular cluster, an RR Lyrae star at its pulsation maximum shines with a brightness that, after crossing that enormous span of space, arrives at a terrestrial telescope as a faint signal well within the range of modern instruments. The measurement that produces a distance estimate from that signal is not glamorous. It is patient and repetitive, requiring many observations spread over many nights, careful calibration of the instrument, correction for dust that lies between the cluster and the telescope and dims the light by a small but non-negligible amount. The distance that emerges from this work is not a dramatic discovery. It is a number in a catalog, quietly confirming or refining a measurement made earlier by different methods. But it is anchored in the physics of a pulsating star, and the reliability of that anchor has been tested many thousands of times across the sky. The RR Lyrae star's steady rhythm, cycling through its brightening and dimming over a period shorter than a single Earth day, has been used to map the three-dimensional structure of the galactic halo, to calibrate other distance indicators, to build one rung of the ladder by which much larger distances in the universe are eventually measured. A single pulsating star, smaller than the Sun, burning helium quietly inside a cluster of 100,000 stars, sweeping its small light variation across 30,000 light-years of empty space, and from that variation, a distance. From that distance, a sense of where the cluster sits within the greater structure of the galaxy. From the position of the cluster and its hundreds of siblings, a rough map of the halo, a three-dimensional picture of the ancient outer territories that surround the flat galactic disk, all of it resting in part on the reliability of a star that dims and brightens on a cycle shorter than the time it takes the Earth to turn once beneath the stars that contain it. The red giants glow amber in the cluster core. The horizontal branch stars hold their quiet equilibrium at temperatures ranging from dull orange to a pale, cold blue-white. The blue stragglers sit above the turnoff in the diagram, their mass borrowed or acquired, burning as though the cluster were billions of years younger than it is. And in the outer regions of the cluster, where the density of stars falls off and the darkness between neighbors grows wider, an RR Lyrae star moves through its cycle in the ordinary darkness between the suns, brightening to its peak and then descending again along that long, slow slope back to minimum, repeating the same period it has kept for millions of years, steady and unhurried and precise, its light crossing an empty that takes 30,000 years to cross, arriving still oscillating, still telling the distance true. In the center of a globular cluster, the light never fully fades. There is no true night there, no rotation carrying one face of a world away from the warmth of nearby suns, because the suns are too many and too close, and their combined glow fills the surrounding space in every direction with something between a deep dusk and a pale amber noon. From far outside, the cluster appears almost still, a sphere of ancient fire compressed by its own gravity into a shape that has been slowly tightening for billions of years. And at the heart of that sphere, something is happening that cannot be seen but can be measured in the way stars move. A long, slow inward fall that has been underway since before the Earth existed. That inward fall has a name: core collapse. It is not an explosion or a rupture. It is something quieter and more patient than either of those. A gradual surrender of heat from the cluster's center to its outer regions, a loss that cannot be replenished fast enough to stop the contraction that follows. The center gives up energy, the outer layers receive it, and because of that slow one-way transfer, the core grows denser, more concentrated, pulled more tightly together with each passing era. In a cluster undergoing this process, the central brightness does not level off into a flat plateau, but continues rising all the way to the smallest scale that any telescope can resolve, a steep and unbroken ascent toward a point that has no visible floor. Roughly 1 in 5 of the Milky Way's globular clusters has passed through this collapse. Their brightness profiles, plotted against distance from center, climb steeply and without mercy. No softening, no central core of stable brightness to announce that the contraction has reached a limit. In these clusters, the inner region has been folding inward for so long that the change is readable not in any single observation, but only across a long comparison of how the light is distributed. The physics calls it a gravothermal catastrophe, which sounds violent, but the process itself is patient enough to be almost gentle. Stars in the center draw closer, the density rises, the gravity concentrating those stars grows stronger still, pulling more inward. It is self-reinforcing, and it is slow, and in a cluster old enough, it proceeds whether or not anything is watching. A star deep inside a collapsing core does not feel itself falling, the way a stone dropped from height feels the rush of air against its surface. Instead, it drifts, moving on a long elliptical path through the cluster, drawn toward neighbors by gravitational nudges too subtle to measure in a single orbit, but accumulating over thousands of orbits and millions of years into a net motion inward. The star is not being swallowed, it is sinking the way sediment settles through still water, slowly and without drama, arriving closer to the center after an immense span of time has passed. Other stars are doing the same. The whole inner cluster tightens, degree by imperceptible degree, while the outer cluster continues its own slower life, mostly unaware. This sinking is part of a broader process called two-body relaxation, which is the gradual reshuffling of a cluster's energy from star to star through a long accumulation of weak gravitational encounters. Two stars pass near one another, each pulls slightly on the other. Their velocities change by a small amount, a tiny fraction of the speed they were already moving. They continue on their separate paths. Nothing visible has occurred, but the exchange happened, and something was transferred, and over the course of thousands of such encounters, spread across millions of years, the individual star's energy has been altered in a way that eventually shows. In the densest cluster cores, this process runs quickly enough, quickly by the standards of gravity across vast time, that the stars have had time to sort themselves. The heaviest stars sink, the lightest rise. This sorting is called mass segregation, and its result is a cluster whose interior and exterior are populated by different kinds of objects. At the center, where the most massive stars and stellar remnants have sunk, the local density is extreme. Farther out, where lighter stars have drifted on the energy they absorbed from gravitational encounters, the population is different, smaller, older, dimmer, each one having received enough of a gravitational nudge over a long history of interactions to occupy a larger orbit. The cluster has not been divided deliberately. No force chose to place each star where it sits. The sorting arose from the same patient physics that drives water down a slope. The slow accumulation of many small effects, each one trivial, each one in the same direction, adding together across time, until the result is unmistakable. In the densest cores, two-body relaxation operates on timescales of tens of millions of years. In the outer halo of a sparse cluster, the same process may take longer than the age of the universe to complete. The outer regions of a cluster are quieter. Stars there move in wider, slower orbits. visited less frequently by gravitational neighbors, and the encounters they do experience are gentler, too slight to move them far in a single pass. But quieter does not mean unchanging. Over the full span of a cluster's life, even the most loosely bound outer stars are engaged by the slow lottery of gravitational exchange, and in that lottery, some stars are unlucky. A star that receives enough energy from a sequence of such encounters will find itself moving slightly faster than before, and then slightly faster still, until at last it crosses an invisible threshold. Beyond that threshold lies freedom and escape. The star is no longer bound. The cluster's collective gravity cannot reach far enough to reclaim it, and so it drifts away, alone, into the larger space of the galaxy, joining the diffuse field of old stars that wander without any single gravitational home. This loss of stars is called evaporation, borrowing the language of thermodynamics, and the comparison is apartment. Just as the molecules that escape a liquid surface are the ones that happen to carry more than their share of kinetic energy at the moment they reach the surface, the stars that escape a globular cluster are the ones that happen to receive, through the random accumulation of gravitational encounters, enough energy to exceed the escape velocity at the moment they reach the cluster's outer edge. The evaporation of stars from a cluster is therefore not a catastrophe, but a kind of slow statistical bleeding, a continuous invisible loss that the cluster sustains throughout its entire life. Most of the stars the cluster was born with are still there, but not all of them, and the fraction that remains decreases very slowly as the billions of years accumulate. There are forces from outside the cluster that accelerate this bleeding. The most significant among them is tidal stripping, the difference in gravitational pull experienced by different parts of the cluster as it orbits through the Milky Way. The galaxy's gravity does not pull equally on every star in the cluster. Stars on the side of the cluster facing the galactic center feel a slightly stronger pull toward it than stars on the far side, and that difference is enough, across time, to peel away the outermost, most loosely bound members. With each orbit the cluster completes around the galaxy, stars from its outer envelope are combed away and left behind along the orbital path, two long, faint streamers trailing ahead and behind the cluster like the wake of a ship moving through deep water. These tidal tails are real structures. They are faint. The individual stars in them are spread across enormous volumes of space, and no single portion of the tail is bright enough to catch the eye the way the cluster itself does. But they are there, readable in maps of stellar positions assembled from careful surveys of the galactic halo. Some tails extend for thousands of light years along the cluster's orbital track, a record of every star lost to the galaxy's pull across billions of years of wandering. The stars in a tidal tail are not in a cluster. They are not bound to one another anymore. They move in orbits slightly different from the cluster's own, drifting apart slowly over time until eventually they will be indistinguishable from any other old star scattered through the galactic halo. The tail is already dissolving. It will take a very long time, but its final state is inevitable. The tidal stripping is worse during the moments in a cluster's orbit when it passes closest to the galactic center, or when it punches through the dense sheet of gas and stars that forms the galactic midplane. These passages are not rare. Most globular clusters orbit the Milky Way on paths that carry them through the plane every few 100 million years, and each crossing is a brief gravitational storm, a sharply increased tidal force that lasts for only a short time, but is intense enough to strip away a small additional fraction of the outer cluster. Over the course of many plane crossings and perigalactic passages accumulated across billions of years, the total mass lost can be significant. A cluster that began with 100,000 stars may now contain only a fraction of them. The rest are scattered across the galaxy, indistinguishable from the halo they have joined. Meanwhile, inside the cluster, a different and quieter drama is taking place at scales too small to observe directly. In the dense core, where stars are packed close enough that interactions are frequent and the timescales of relaxation are short, binary star systems play a role that is difficult to overstate. A binary system is two stars orbiting one another, bound tightly together by their mutual gravity. In the wide, sparse environment of the galactic field, binaries are common and largely unremarkable, but in the compressed heart of a globular cluster, a tight binary system becomes something else entirely, a reservoir of energy, coiled and patient, releasing heat into the cluster, one gravitational encounter at a time. When a single star passes close to a binary pair, the three-body encounter that results is chaotic in its details, but statistically predictable in its outcome. The interloping star is flung away from the encounter with a higher velocity than it arrived with, carrying energy that came from the binary's own orbital binding energy. The binary responds by tightening, the two companion stars drawing closer together, their orbit shrinking, their binding energy deepening. The next interloper to arrive will find an even tighter binary, holding more energy, capable of imparting an even larger velocity kick. The binary grows harder with each encounter, releasing more energy each time, and the stars it ejects carry that energy outward into the surrounding cluster. This is the mechanism that holds back the gravothermal catastrophe. As the cluster's core contracts and heats, the rate of three-body encounters involving hard binaries increases. More energy is released. More stars are kicked outward. The outward pressure of these ejected stars pushes back against the inward contraction, not through any deliberate resistance, but through the same physics that prevents a gas from collapsing under its own weight when it has enough thermal energy to push back. The core oscillates, contracting, then re-expanding slightly as binary energy heats it, then contracting again in a rhythm that continues as long as the supply of hard binaries lasts. In clusters where this mechanism operates effectively, the central brightness profile shows a distinct flat core, a region where the contraction has been arrested and the density has stabilized. Those clusters are distinguished from their core collapse neighbors by this single visible feature, a softening at the center, where hardness would otherwise be expected. The stars that receive the largest velocity kicks from binary encounters do not necessarily escape the cluster entirely. Many of them are flung outward to the intermediate and outer regions of the cluster, arriving there with excess energy that they then share with neighboring stars through further encounters. Some of that energy eventually propagates all the way out to the outer halo, nudging loosely bound stars a little faster, contributing to the slow drip of evaporation. The cluster is a connected system, and what happens at the center is not isolated from what happens at the edge. Energy generated by a hard binary in the core can, through a long chain of interactions spread across millions of years, eventually carry a star at the outer boundary across the threshold of escape and into the galactic field. In the densest clusters, the stellar density at the core can reach values where stars are separated from one another by distances smaller than the diameter of the solar system, a situation so compressed that by the standards of interstellar space, the stars are nearly touching. In such environments, the rates of close stellar encounters are high enough that over a cosmological timescale, Direct physical collisions between stars become not just possible, but expected. Two stars whose trajectories bring them within a critical distance will not simply exchange a gravitational nudge and continue on their way. They will merge. Their outer layers will interpenetrate, heat will dissipate, and what was two separate stars will become one, larger, more luminous, more massive than either of its progenitors, and occupying a region of any plot of stellar properties where no star of the cluster's age should naturally reside. The cluster produces these unusual objects continuously at low rates across its entire life. The compact object population that accumulates in a cluster core over billions of years is dense in a different way. Neutron stars, left behind by supernovae, white dwarfs, the cooling embers of stars that exhausted their fuel and shed their outer layers. In some clusters, stellar mass black holes, the collapsed remains of the most massive stars, may still be present in large numbers, having settled into the core through the same mass segregation that affects all heavy objects. These remnants interact with one another and with ordinary stars through the same gravitational exchange processes that govern the rest of the cluster's dynamics, but because they are dense and compact, their encounters can produce exotic outcomes. X-ray binary systems, in which a compact object is drawing material from a normal stellar companion through gravitational accretion, are found in globular clusters at rates far higher than in the general galactic field. The cluster's high stellar density makes the formation of such pairings far more likely than it would be in the sparse neighborhood of an ordinary galactic region. There is, at the centers of some of the most massive and compact globular clusters, a question that the measurements have not yet settled. The velocity dispersion of stars, how fast they are moving relative to one another, can be mapped across a cluster's face using spectrographs sensitive enough to detect the tiny shifts in starlight caused by each star's individual motion toward or away from the telescope. In many clusters, this dispersion rises and falls smoothly, with distance from the center, behaving in a way that can be fully explained by the mass and distribution of the stars alone. But in a smaller number of clusters, the dispersion shows something different, an upturn at the very center, a slight but real increase in how fast the innermost stars are moving, above and beyond what the visible stars themselves could produce. That excess velocity requires an explanation, and one of the explanations that has been offered is the presence of an intermediate mass black hole, an object too small to be among the supermassive black holes found at the centers of galaxies, but far too large to be a black hole left by any single dead star. Its mass would fall somewhere between 100 and 100,000 times the mass of the Sun. The case for such objects is not settled. The velocity signal, even when it is present, is subtle, confined to the innermost few light years of the cluster, where the individual stellar motions are hardest to separate cleanly from one another, and where the combined effects of many ordinary stars moving in many directions can mimic, at some level, the signature of a single massive hidden object. Alternative explanations exist and are taken seriously. A concentrated swarm of massive stellar remnants, neutron stars, and black holes that have sunk to the center through mass segregation can produce a velocity upturn that resembles the signal expected from a single large black hole, without requiring that any single massive object be present at all. The instruments available now are just barely sensitive enough to see the signal, and not yet sensitive enough to distinguish cleanly between the explanations that could produce it. The question remains open, and it does so calmly, the way most deep questions in this field remain open, held in place by the limits of what can be seen. waiting for the next generation of instruments to shift the boundary slightly further inward. There is something fitting in this uncertainty. The globular cluster is itself a system of accumulation, of stars gathered over billions of years, of encounters layered on encounters, of slow processes building consequences too large to observe in a single human lifetime. And at its deepest center, after all that time and all that compression, the ultimate state of matter may be hidden in a form that current instruments cannot yet fully resolve. The cluster has been at this for 11 billion years. The uncertainty at its center is not a failure to understand. It is a boundary, and boundaries in this field have a way of retreating. A star in the outermost halo of an old globular cluster moves slowly, now on a path that has been widened over time by the small energy gains accumulated through many gravitational encounters. Its orbit carries it far from the center and back, looping out into the galaxy's general space before falling inward again across a path that takes hundreds of millions of years to complete. On one such outward swing, the tidal forces of the Milky Way may stretch its orbit slightly further than before. On the next passage through the galactic plane, a brief gravitational surge may give it the small additional push it needs. And then one day, on a time scale that makes the word day feel almost comical, the star will not fall back. Its inward path will shallow and then level, and the cluster will no longer be able to call it home. It will drift into the halo, joining the enormous population of old scattered stars that surround the galaxy in a diffuse cloud, indistinguishable from any other halo star in composition or in age, carrying no visible record of the cluster it came from. The cluster will not notice. It will continue its orbit. Other stars will continue their slow exchange of energy through gravitational encounters, continuing the long redistribution that has been underway since before the solar system formed. Hard binaries will continue to tighten and to heat the surrounding stars with each encounter. The core, if it has not already collapsed, will continue its slow inward drift. And in the deep interior, the compact objects will continue to move through the dense stellar traffic of the core, pairing and interacting, and occasionally merging in ways that no human instrument has yet witnessed, at the scale and resolution needed to resolve them clearly. A globular cluster lives long, not forever, but long enough that the word long begins to lose its ordinary meaning. Most clusters will survive for many more billions of years before evaporation and tidal stripping have taken enough of their stars to dissolve them entirely. The most compact, most massive clusters, those whose high density slows the rate of evaporation and whose deep binding energy resists the galaxy's tidal pull, may persist for tens of billions of years, longer than the current age of the universe, drifting through a galaxy that will itself have changed beyond recognition by then. They are not permanent. Nothing is permanent. But in the context of the universe's current age, they are very nearly so. What the cluster has been doing all this time is finding a balance. Not a static balance, not the stillness of something that has stopped moving, but the ongoing dynamic balance of a system in which the forces pulling inward and the forces pushing outward have reached a kind of negotiated equilibrium that continually adjusts without ever fully resolving. The core contracts, binary energy heats it back, stars evaporate. The cluster's density profile reshapes itself slightly to compensate. The galaxy peels away the outer halo. The cluster's inner regions remain intact. It is a system that has been adapting to its own losses for billions of years, quietly, without any single dramatic turning point, each adjustment a response to the last. In this sense, the cluster is not dying. It is simply aging, the way everything in the universe ages, through a long sequence of changes that each leave it slightly different from what it was before, while still recognizably itself. Far from the cluster's center, far enough that the dense stellar background has thinned to a scatter of individual points, each one separated from its neighbor by distances measured in fractions of a light year. The outermost stars move in a kind of solitude. They are still bound, barely. The collective gravity of the hundreds of thousands of stars deeper inside still holds them, faintly, on orbits so wide and so slow that an entire human civilization could rise and fall in the time it takes one of them to complete a single revolution. They do not know they are in a cluster, in any physical sense. They experience only the faint diffuse pull of the whole, distributed across the space around them, holding them just inside the threshold of escape. For now, the tidal tails that stream away from the cluster's orbital path mark the places where that threshold was crossed. Each star in a tail was once like the outermost bound stars, barely held, slowly gaining energy, approaching the limit. Then it crossed. The crossing was not violent. It was gradual enough that the star's trajectory changed only slightly, its path curving away from the cluster's gravitational center by a tiny angle that over many millions of years became a separation large enough to be called departure. The star moved on, the tail grew longer, and the cluster moved on as well, somewhat lighter, continuing its orbit around the center of the galaxy, as it has been doing since long before the Earth was formed from the collapse of a distant cloud of gas. In the direction of the galactic center, the cluster's orbit brings it periodically through the most crowded and gravitationally intense region of the Milky Way. The passes are brief by astronomical standards, a few tens of millions of years, but during each one, the tidal forces are at their strongest, and the rate of stripping is highest. Stars pour from the cluster's outer halo, like water wrung from cloth. The cluster emerges from each pericentric passage, slightly smaller, slightly more compact, its outer layers left behind in a diffuse wake, and then it climbs back out toward the halo, where the galaxy's tidal influence weakens, and the stripping slows to a faint residue, and the cluster has time to resettle into its own slower dynamics before the next inward plunge begins. This is the rhythm of its life, inward and outward, over billions of years. Dense core and dispersing halo, hard binaries releasing heat, and loose outer stars releasing their grip. The cluster is a machine, in the sense that it operates through physical laws that do not change. But it is also something quieter than a machine, a structure that has found a way to persist through time by continuously adjusting to every force that acts upon it, without any mechanism designed to achieve that persistence. It simply works that way. The physics allows it, and so it endures. Somewhere at the center of that enduring sphere, in a region too dense to resolve cleanly with instruments now in existence, something waits. Whether it is a single massive object or a concentrated swarm of smaller ones, whether it is a black hole of intermediate mass or only the dense residue of mass segregation played out across cosmic time, the measurements do not yet say clearly. The velocity of the innermost stars rises, slightly, toward the center. The brightness of the innermost region climbs without leveling off. Something is there, in the densest part of the densest structure in the galaxy's orbiting retinue, something that the cluster has been building toward or harboring for billions of years. What it is remains, for now, a calm and open question. The cluster does not resolve it. It only holds it at its center, in the dark behind all that compressed light, surrounded by stars so close together that the space between them is smaller than the distance from one planetary system to another. Patient, ancient, and very nearly still. The outermost star in the cluster's halo drifts on its wide, slow arc, barely inside the boundary that separates belonging from departure. The core, far below it in the gravitational architecture of the cluster, continues its long inward motion. The hard binaries at the center continue to tighten and to release their small packets of heat. The tidal tails extend quietly along the cluster's orbital path, each star in them a little further from the center than it was before, moving on into the general halo of the galaxy with the unhurried permanence of something that has already finished its long transition and settled at last into the vast and patient dark. In the spectrum of a single ancient star, folded and narrow as a thread of light drawn through a prism, there is a gap where a particular wavelength of oxygen should appear. The gap is not empty by accident. It marks a place in the star's outer layers where oxygen was present in slightly lower abundance than the surrounding atoms of iron and silicon, and hydrogen, not dramatically lower, but measurably so, in a way that a precise instrument can read as clearly as ink on a page. That diminishment was written into the star at its birth, when the cloud of gas that became it was already carrying a particular chemical history, the record of what had burned and scattered before any of these stars were made. The star has held that gap, that slight quieting of a single wavelength, for 11 billion years, and in that holding it has kept something the universe would otherwise have lost. The alpha elements, oxygen, magnesium, silicon, calcium, are made by massive stars burning quickly through their fuel. A star 10 or 20 times the mass of the Sun exhausts its core in a few million years, far short of what smaller stars endure, and when it collapses and rebounds into a supernova, it scatters those elements outward at millions of miles per hour into the surrounding gas. The enrichment is rapid. It happens on the time scale of the stars that cause it, which means it is geologically swift, cosmologically brief, completed within the first billion years of a galaxy's life, before most of its stars are even formed. Iron arrives later and more slowly, built not in the cores of the most massive stars, but in the thermonuclear runaway of white dwarfs, accreting from companions, events that take billions of years to accumulate in meaningful numbers across a galaxy. So in the earliest stellar populations, the ratio of alpha elements to iron is higher than it is in younger stars, not because oxygen and magnesium are more abundant in some absolute sense, but because iron had not yet had time to catch up. The supernovae that made iron were still in the future when these stars were already old. In the spectra of metal-poor globular cluster stars, this imbalance is preserved with great clarity. Oxygen and magnesium and silicon sit at abundances that tower over iron relative to what younger stars carry. The ratio tells a story. It says that these stars, condensed from gas enriched by the earliest round of core collapse supernovae, before the slower iron factories had time to contribute, before the interstellar medium had accumulated anything like its present chemical richness. The measurement is a kind of timestamp, not on a page or a stone, but written in the proportions of nuclei suspended in the outer layers of a star that is still burning today, still fusing hydrogen into helium in its deep core, still carrying the composition it received at birth, unchanged and intact through 11 billion years of slow, steady fire. A single stellar spectrum, when recorded at high resolution, resolves into hundreds of absorption lines, each one a signature of a particular element at a particular energy state. The astronomer who reads it is not reading language in any metaphorical sense. Each line is a physical imprint, a wavelength subtracted from the continuum by atoms in the stellar atmosphere, absorbing and re-emitting at their characteristic frequencies. Among all those lines, the pattern of alpha element enhancement is not obvious to a casual eye. It requires comparison, calibration, a model of what the abundances should be if the star had formed later in a more chemically evolved environment. Against that baseline, the departures become visible, small but unmistakable, each departure a number, and each number a piece of a story about the first billion years of cosmic star formation. The star is not aware that it carries this record. It is simply old, and in its oldness it has not changed. Most of the stars visible to the naked eye on any given night formed billions of years after the oldest globular cluster members. They carry the accumulated contributions of many stellar generations, the oxygen from one round of supernovae, the carbon from the gentle winds of dying intermediate stars, the iron from white dwarf explosions spread across galactic time. Their compositions are rich and varied, carrying the layered chemistry of a galaxy that has been recycling its material for most of the age of the universe. The stars inside the oldest globular clusters formed before most of that layering had occurred. They were born into a universe that had only just begun the long work of making its heavier elements, and their spectra showed that earliness in every line. Among the more arresting things found inside globular clusters in recent decades is the discovery that many are not the simple stellar populations they were long assumed to be. For most of the history of stellar astrophysics, a globular cluster was understood as the closest thing nature provided to a single burst stellar system. All the stars inside it formed at roughly the same time, from the same gas, with the same initial composition, making the cluster useful precisely because its stars shared a common age and origin. That picture was clean and tractable and useful for a long time. The evidence that dismantled it came slowly from increasingly sensitive spectrographs measuring faint differences in the light of stars that appeared almost identical in every other way. Within a single well-studied cluster, separated by nothing more than their position in the cluster and their slightly different light, differences so subtle that decades of observation failed to separate them from noise. There are stars with normal oxygen and low sodium, and stars with low oxygen and high sodium. The pattern is not random, it is structured. Oxygen and sodium move against one another in a precise and reproducible anticorrelation. When one is higher, the other is lower, as though the two elements were being traded between two populations by a process operating inside the cluster itself after the initial stars had already formed. Magnesium and aluminum show a similar paired variation, with magnesium declining as aluminum rises. This is not a feature of the interstellar medium from which the cluster formed. It is something that happened inside the cluster, among its stars, in the first 1,000,000,000 or 2 years of its existence. The leading picture is one of an internal recycling event. A first generation of stars formed from the original cloud. Among those first generation stars, the most massive and the most luminous, perhaps asymptotic giant branch stars, perhaps rapidly rotating massive stars, expelled material from their outer layers through stellar winds, material that had been processed through high-temperature nuclear reactions in their interiors, reactions that produce sodium and aluminum at the expense of oxygen and magnesium. That processed gas pooled in the gravitational center of the cluster, mixing with the surrounding pristine gas, and from that mixture, a second generation of stars formed. The second generation stars carry the chemical signature of what they were made from, enriched in sodium, depleted in oxygen, carrying the fingerprints of the nuclear furnaces of their predecessors. Both populations are old, both formed at a time the universe was young, but they formed at slightly different moments, from slightly different material, and that difference is still readable in their spectra today. The existence of multiple stellar populations inside a single globular cluster has revised the way the structures are understood at a fundamental level. They are no longer simple, they are stratified, carrying at least two and sometimes more chemically distinct cohorts of stars that share a common space and a common gravitational well, but carry different records of their origin. Working out the full sequence of events that produced this chemical patterning inside a gravitationally confined system, only a few tens of light years across, has occupied observers and theorists for years, and the full picture remains to be settled. What is clear is that the cluster is not a single thing. It is a layered thing, and its layers are chemical, not physical, invisible to any instrument that cannot parse the fine structure of stellar light. The anti-correlation pattern, oxygen falling as sodium rises, magnesium falling as aluminum rises, is not found in field stars of the same age and metallicity scattered through the galactic halo. It is specific to stars that formed inside dense, gravitationally bound clusters, where the processed ejecta of early stars could be retained and mixed into new star formation before the cluster dispersed. It is a signature of a particular environment, compact, dense, gravitationally deep, capable of holding on to the gas shed by its own massive stars long enough for a second round of star formation to begin. Open clusters, smaller and more loosely bound, could not do this. Their gas escaped too quickly, and they preserve no such internal recycling signature. The chemical patterning is itself evidence that the conditions inside early globular clusters were unusually dense and retentive, capable of a kind of internal chemical evolution that the diffuse galactic field could never sustain. Far outside the cluster's gravitational reach, at distances where the light of the cluster is already beginning to fade into the general glow of the surrounding halo, there are galaxies tens of millions of light years away, whose own globular cluster systems can be studied, not star by star, but collectively, measured in statistical arrays of cluster brightnesses detected against the faint background of the host galaxy's extended disk or halo. In a single pointing of a large telescope toward a nearby elliptical galaxy, the detector will record dozens or hundreds of point sources, too compact to resolve, their light integrated into single measurements, their distances unknown in any direct sense. But among all those detected points, the distribution of their brightnesses follows a pattern that is the same in every galaxy, where it has been carefully measured. If the clusters are sorted by how bright they appear, how much light they deliver to the detector per unit area, and counted into brightness bins, the resulting distribution rises and falls in a specific and consistent shape, peaking in a particular apparent magnitude that represents the most common kind of cluster, the cluster at the midpoint of the population in terms of total stellar content. That peak is always found at the same intrinsic luminosity and absolute brightness in the visual band that corresponds to a cluster containing a few 100,000 solar masses of stars, bright enough to outshine any single star in its host galaxy by many thousands of times, but modest enough by extragalactic standards to be thought of as a reliable average, because the peak luminosity is consistent, not merely consistent in the Milky Way, not merely consistent in nearby galaxies, but consistent across the full accessible population of globular cluster systems in dozens of galaxies measured over decades of observation. It can be used as a measuring stick. The logic is simple and old. If a candle always burns with the same intrinsic brightness, then its apparent brightness tells you how far away it is. A bright candle far away will look the same as a dim candle nearby. But if you know both are candles, both burning at the same power, then the apparent brightness is pure distance. The globular cluster luminosity function's characteristic peak is that known brightness. An astronomer measuring the apparent magnitude of the peak in a distant galaxy can compute how much farther the peak has been dimmed by travel across space, and from that dimming, compute a distance. The distance to the galaxy that emerges from this calculation does not depend on a chain of intermediate steps. It does not require knowing the distance to another galaxy, or calibrating from a nearby Cepheid variable, or extrapolating from local measurements to remote ones. It is a direct comparison of known brightness to observed brightness across a gap of tens of millions of light years, a gap that no probe has crossed and no signal but light has ever bridged. The measurement carries uncertainties. Cluster populations vary somewhat between galaxy types. The mass function of clusters at the time of formation was not precisely uniform across all environments, and the effects of time on cluster populations, evaporation of the lowest mass clusters over billions of years, dynamical friction drawing the most massive clusters inward, may have shaped the luminosity function differently in different settings. These are small corrections, understood in general, if not in every particular, and they are accounted for in the distance estimates that come from this method. The distances that emerge from measuring the globular cluster luminosity function in dozens of galaxies have consistently matched and extended the distances established by other means, including the brightness of individual old stars at the tip of the red giant branch, and the period luminosity relationship of Cepheid variables in the same galaxies. That consistency across independent methods, each anchored to different physics, each subject to different systematic errors, each arriving at the same answer within its stated precision, is the deepest form of confidence available in any empirical science. The distances built from globular cluster populations feed into the larger project of measuring how fast the universe is expanding. The Hubble constant, the number that relates a galaxy's recession velocity to its distance, the scaling factor that tells cosmologists how old the universe is, and how large the observable portion has become since the beginning. The consistency between distances measured from globular clusters and distances measured from other methods has been a quiet confirmation of the overall framework of modern cosmology, a check performed at the level of individual resolved point sources in galaxies tens of millions of light years away, and passing that check each time. The oldest globular clusters also offer the universe's age directly and independently through a method that requires no assumption about cosmological expansion at all. The stars inside the oldest clusters are still burning, still present, still available for measurement with a large enough telescope. On a diagram that plots stellar temperature against stellar luminosity, the oldest cluster members form a distinctive pattern, a long curving sequence of hydrogen-burning stars arranged from hot and bright at one end to cool and faint at the other, ending at a point called the main sequence turnoff, where the pattern bends away as the most luminous of the remaining hydrogen-burning stars begin to exhaust their cores and swell into the evolved states that follow. The location of that bend is a direct function of age. A freshly formed cluster has its turnoff at high luminosity and high temperature because even the most massive and rapidly burning stars have not yet had time to exhaust their cores. As the cluster ages, the most massive stars among the still burning sequence exhaust themselves first and depart, and the band moves to lower luminosity and lower temperature. The remaining stars, slightly cooler and slightly less bright than the ones that burned out before them. The position of the turnoff is a clock, and the clock has been running since the cluster formed. For the oldest Milky Way clusters, the turnoff falls at a luminosity roughly equal to that of the Sun, at a surface temperature only slightly higher than the Sun's own. Modest stars, faint by the standards of the more massive cluster members that departed long ago, burning slowly and lasting well. The theoretical models of stellar structure and evolution that predict where the turnoff should fall for a star of a given mass, composition, and age are among the most precisely tested in all of astrophysics, calibrated against the Sun's own properties, tested against clusters of known composition at a range of metallicities, revised over decades of computation and observation. When those models are applied to the oldest clusters and the turnoff position is read against the age scale they provide, the answer that comes back is between 11 and 13 billion years. The oldest clusters formed when the universe was already several hundred million years old, and the universe itself, on the basis of an entirely independent measurement, the temperature pattern of the cosmic microwave background, the oldest light, carrying the geometry and contents of the very young cosmos, is approximately 13,800,000,000 years old. The two numbers are consistent. The lower bound set by the clusters fits comfortably inside the upper bound set by the background radiation, with room to spare. If the clusters had come back older than the universe, something fundamental would have been wrong with one or both measurements. They did not. The consistency is quiet confirmation that both measurements are tracking something real, that the physics that governs distant ancient stars is the same physics that governed the cooling of the very early universe, that the same set of rules applies across a range of scales and conditions no controlled experiment could ever reproduce. A star in the outer halo of the Milky Way drifts on a wide elliptical orbit, tracing a path that takes it far above the galactic plane and back through the disk over the course of hundreds of millions of years. In the 2010 to the Gaia space mission began recording the precise positions and motions of more than 1 billion such stars. Not globular clusters at great distances, but individual resolved stars, close enough to measure their annual sideways drift against the distant background, a drift called proper motion, small enough that it takes precision greater than any ground-based telescope achieves to detect it. Alongside those individual stars, Gaia measured the proper motions of the globular clusters themselves. The sideways drift of each cluster as a whole, averaged across all its individually unresolved members, sufficient to determine the full three-dimensional velocity of each cluster through the Milky Way's gravitational field. With a full three-dimensional velocity, sideways motion from Gaia, motion along the line of sight from ground-based spectroscopy, distance from the luminosity function, or the red giant branch tip, the complete orbital trajectory of a globular cluster can be computed backward through time, following its path under the influence of the Milky Way's gravitational potential, as that potential is currently modeled. The orbit that emerges may be a gently inclined near circle, like many clusters, or a sharply plunging elongated ellipse that carries the cluster deep into the galactic center and far out into the distant halo on each pass, or an orbit nearly perpendicular to the galactic plane, inclined steeply against the rotation of the disk. When the computed orbits of many clusters are examined together, not individually, but in their ensemble, patterns emerge. groups of clusters share similar orbital inclinations, similar orbital energies, similar angular momenta. They travel in related directions. Their orbits, traced back to a common origin, converge. The interpretation that best accounts for this clustering in orbital space is not coincidence. A group of clusters on similar orbits most likely fell into the Milky Way together, embedded in a common host, a dwarf galaxy that was gravitationally disrupted as it merged with the Milky Way billions of years ago. The host galaxy is gone. Its stars have long since dispersed into the general halo population, mixed beyond separation, with the halo stars formed in place by the Milky Way's own early collapse. But the clusters it carried, being dense and tightly self-gravitating, survived the disruption of their host intact, continuing to orbit as coherent objects, while everything around them dissolved. What remains of the dwarf galaxy, then, is not a shape, not a stream of stars that can be traced in the sky, but a pattern in orbital space, a cluster of trajectories in the abstract space of energies and angular momenta, identifiable only when the full three-dimensional kinematics of the surviving clusters are known and their orbital paths are computed. The merger event, thought to account for the largest such concentration of kinematically related clusters, is one that occurred between 8 and 11 billion years ago, during a period when the young Milky Way was still assembling itself through repeated collisions with smaller systems. The dwarf galaxy involved was massive enough to have made a significant contribution to the Milky Way's interstellar halo. Perhaps as much as half the halo's total stellar mass came from this one event, making it not a minor accretion, but a foundational collision, a merging that partly defined the galaxy that exists today. The globular clusters that arrived with it were already ancient by the time they fell in, having formed inside the dwarf galaxy in its own earliest era, billions of years before the merger. They have now orbited the Milky Way for longer than the time between the formation of our solar system and the present day, and they will continue to orbit for far longer still, carrying the orbital signature of their origin in a system that no longer exists anywhere else in any form. The stars of the disrupted dwarf galaxy do not announce themselves in the sky. They look like any other old metal poor halo stars, scattered through the vast diffuse sphere of ancient light that surrounds the Milky Way's disk. Without kinematics, without knowing how they move, there is no way to separate them from the stars formed in the Milky Way's own earliest collapse. But the clusters are different. They retained their coherence. They can be tracked. Their trajectories, once measured, can be traced to a common origin, and from the orbital properties of that origin, the properties of the lost dwarf galaxy can be partially reconstructed: its mass, its orbit, the depth of its gravitational well, the range of metallicities its clusters carry. The clusters are the legible remnant of a vanished galaxy, the only form in which that ancient merger has left something that can still be identified and studied as a discrete trace in the present-day Milky Way. Other merger events, smaller and older, have left their own clusters behind. The full population of Milky Way globular clusters, some 150 known members, ranging from massive, dense systems orbiting deep in the inner halo to sparse, extended systems wandering the far outer reaches, is now understood to be a mixed population, partly formed in the Milky Way's own early collapse, partly accreted from a series of dwarf galaxies consumed over billions of years. The division between these two origins is written partly in the metallicities of the clusters, which show a bimodal distribution: two peaks, one at lower metallicity, associated with the outer halo, and a history of accretion, one at slightly higher metallicity, associated with the inner halo, and the early Milky Way itself, and partly in the orbital properties revealed by Gaia, which allow individual clusters to be tentatively assigned to the merger event most likely responsible for their arrival. The history of the Milky Way's early assembly, a history that no direct observation of the early universe from Earth could ever reconstruct at this level of detail, is partially readable in the distribution and kinematics of its surviving globular clusters. In the darkness between the clusters themselves, in the wide empty halo through which they orbit, there are old stars that are not clustered. They drift alone, or in loosely associated streams, or in the broad, undifferentiated population of the halo, each one following its own long elliptical path around the galaxy's center. Some of these stars were always solitary, born in the early Milky Way's own halo, never part of any cluster, forming from gas that collapsed directly into stars, too dispersed to organize into a self-gravitating system dense enough to survive. Others, perhaps many, were once cluster members that were gradually stripped away by tidal forces during the cluster's repeated passages through the galactic disk, or energized by gravitational encounters inside the cluster to velocities above the escape threshold, and so released into the halo to orbit alone. They carry the same chemical signatures as their former cluster members, the same alpha element enhancement, the same low metallicity, in some cases the same light element anti-correlation patterns that mark a second-generation cluster star, but they are no longer bound to anything. They have become the diffuse halo by the very processes that make the clusters slowly smaller over time. The contrast between a globular cluster and the diffuse halo it moves through is not merely a contrast in density. It is a contrast in coherence, in the degree to which a structure has held itself together against the long, patient erosion of external tidal forces and internal dynamical evolution. The diffuse halo is what results when coherence fails or was never achieved. Individual stars on individual orbits, related by their origin in the same general epoch of galaxy formation, but no longer connected to one another by anything but that shared history and the shared gravitational field of the galaxy as a whole. A globular cluster, orbiting through that same halo, has maintained something the halo has not, a self-contained gravitational order, a density sufficient to hold its members together against the galaxy's tidal field, a coherence that has persisted across 10 billion years and more of repeated orbital passages, tidal stripping, and the slow thermodynamic mixing of its own internal dynamics. That the clusters are still here, still dense, still compact, still visible as distinct objects against the surrounding halo of diffuse light, is itself a form of evidence about how tightly bound they must have been at birth, tight enough that even the long erosion of galactic time has not yet dissolved them. On a clear night, far from the lights of any city, the halo reveals itself as a kind of glow gathered around the bright band of the disk, not a uniform glow, not a second Milky Way, but the accumulated light of billions of individual old stars, too faint and too dispersed to resolve into separate points from the ground, merging into a background luminescence that deepens toward the galactic center and thins toward the poles of the galaxy's plane. Against this background, a globular cluster is a different kind of object. It is concentrated. It has a center. In a moderate telescope, even a modest globular cluster resolves toward the edges into individual pinpoints, while the center remains a compressed blur of overlapping light, not because the stars there are unresolved in principle, but because they are simply too close together, too many concentrated into too small an area for the optical path to separate them cleanly. That central blur is real. It is what it appears to be, a place where many suns occupy a volume of space that, by the standards of the surrounding galaxy, is extraordinarily crowded. The innermost core of a dense globular cluster, on the scale of a few light years across, contains tens of thousands of stars, sometimes more. In the Milky Way's neighborhood, a comparable volume of space contains a single star, the Sun, with the next nearest star lying more than 4 light years away in any direction. In the cluster core, those separations collapse by factors of thousands. Stars still do not touch. The distances between even the most closely packed cluster stars, even at the dense core, are measured in fractions of a light year, many times greater than any individual star's diameter. But the sky seen from within that core would look nothing like the sky seen from the vicinity of the sun. There would be no empty darkness punctuated by isolated bright points. There would be a brightness distributed across much of the visible sky, thousands of stars visible in every direction, many of them brighter in the cluster sky than any star ever appears from our own quiet corner of the galaxy. The collective light of the cluster's core casting a faint but pervasive glow that never fully dims into anything that could be called night. That interior sky, blazing with ancient light, is not witnessed by anyone. There are no planets known inside globular clusters, no confirmed systems of the kind that might support the conditions for observation. The density and age of the environment work against planetary stability. Repeated gravitational interactions over long timescales destabilize planetary orbits, and the low metallicity of the cluster's stars means that the solid material from which rocky planets are built was scarcer when the cluster formed than it is in the younger, richer regions of the galaxy, where most confirmed planets reside. The blazing sky of the cluster core exists without observers. It burns in the interior dark, ancient and indifferent, the accumulated light of 100,000 suns suspended in a volume of space that the galaxy's more sparsely populated regions would not fill with even a single star. It has been burning this way for billions of years, through the full span of Earth's history, through the rise and extinction of every dynasty of life that has come and gone on this planet, through all of human time, which is to the cluster's age as a single breath is to a long, slow sleep. What the cluster carries is not a message addressed to anyone. It is simply a record, chemical, structural, orbital, dynamical, of conditions that no longer exist anywhere in the present-day universe in the same form. The dense, cold, turbulent molecular clouds from which the cluster formed are gone, converted long ago into stars. The dwarf galaxy that may have hosted some clusters before delivering them to the Milky Way is gone, dissolved into the halo it helped to build. The chemical environment of the early universe, almost nothing but hydrogen and helium, traces of lithium, with only the faintest beginning of the heavier elements, no longer exists anywhere that stars are still forming today. The universe that made these clusters is not accessible by any means other than the clusters themselves, which have carried their record of that time forward through all the intervening billions of years and delivered it intact to the present, where instruments can read it. A spectrum gathered from an ancient cluster star, falling as a narrow ribbon of sordid light across a modern detector, carries oxygen and magnesium in the proportions they had in the earliest supernova ejecta, a Hertzsprung-Russell diagram of the same cluster, its main sequence bending away at just the luminosity and temperature predicted for an 11 billion year old system, reads the age of the universe from within. A set of cluster orbital trajectories, computed from proper motions measured by a satellite orbiting a planet that did not exist when the clusters formed converge on the ghost of a galaxy that has not existed for nearly as long as life has been on Earth. All of this is contained in spheres of ancient light, a few tens or hundreds of light years across, bound by gravity, scattered through the halo, orbiting patiently in the dark. The halo itself surrounds the galaxy on all sides, thinning as it extends outward, each of its billions of individual wandering stars following its own slow path, alone and unbound to anything but the gravity of the whole. Through that diffuse and ancient light, the clusters move. They are distinct from it, held together by something the halo has lost: the density, the self-gravity, the coherence of their origin, and they carry within them, compressed and preserved, the chemical record of the universe before it was as rich or as complex or as populated as it is today. They orbit and will continue to orbit for longer than the sun has left to burn. The stars within them have been burning since before the solar system existed, will still be burning when the sun is gone, will still be burning when the stars now forming in the bright clouds of the galaxy's spiral arms have lived their full lives and faded into cinders. The clusters are not finished. They are old, and they continue, and they do not require anything to witness them to go on. In the long, quiet arc of a cluster's orbit, rising out above the galactic plane and curving back down through the disk and through the halo on the other side, fully covering hundreds of light years in each direction, over the span of hundreds of millions of years, there is no event, no threshold, no moment at which something changes. The orbit continues because it has always continued, because the gravity that set it in motion has not diminished, because there is nothing in the path of the cluster sufficient to stop it.